This is my first in my video series on forces, and here we're going to look at Isaac Newton's 3 laws of motion, but we're going to stick to the first 2 in this video. Just knowing a little bit more about Newton's important, and you see Neil deGrasse Tyson does a 2-minute video just introducing how important Isaac Newton was. It's good idea to watch this. I'll put this in my information about this video at the bottom. Just looking at what forces and what Newton was talking about. So Newton was talking about forces, and force is any push or pull. So you see this guy pushing that container, you see this guy pulling that container. Either way, they're applying a force to do that. Some of the variables from today's lesson, just to review. Force, this is a new one here. We're going to be using the Newton, and F is going to be the variable we'll be looking for. Mass is another new one, and that's going to be kilogram or kg. So if we're using force or mass, we want to make sure we're in kilograms. We want to make sure that in order to have a Newton is actually equal to a kilogram times meters per second squared. We're going to see the F equals ma later on. Force is Newton, mass is kilogram, acceleration is meters per second squared. So in order to have a Newton, we need a kilogram times the meters per second squared. If you don't have those units, you need to make sure you convert to those units. And then everything else is just what we've covered before. Okay, so something you're going to see a lot of are force diagrams, and they represent all the forces on an object. And here you have the box sitting on a counter. And the box has weight, which is just the force of the earth pulling down on that box. And if it's sitting on a counter, it's not accelerating. Force causes acceleration, by the way. But it's not accelerating, speeding up, just like something dropped through the air, because there's this counteracting force pushing back up. Truly, it's horizontal for harder problems. It's pushing up horizontal to the surface, and this happens to be a 90, the horizontal surface, so it's just pushing straight up. And if you apply a force, which I'll use the unit F or the variable FA to imply, it often will cause a backup force. When the force is applied, there's often going to be the rubbing force between rough surfaces, and that's going to be the force of friction, kind of going in the reverse direction of the applied force. Okay, so this is just more of what I just said a second ago. You got weight, FW, Fn, normal force, Fa, applied force, Ff, force of friction. And then the thing to note is that all of these will have the unit, since they're force, the unit is the Newton. Okay, and then another thing you're going to see a lot of is net force. Net force is just an overall force. So if I take a look at all of these right here, my force applied, my force of friction, my normal force, my weight. Normal force counteracts weight. Force of friction tries to counteract the force applied, but in this case, it's not. So the weight here and the normal force are counteracting. So we're going to ignore those in the net force, which is just an overall force. But this force applied to the left is not completely counteracted by this. So what you have to do is, just like vectors, you have one to the left. You might say minus 75 newtons. And you have one to the right. So I'm going to add up plus 35 to that. And I get a total of, and then the next slide you see, a net force of 40 newtons to the left. And so net force just means, let's not look at all of this, but what is the end result? And net force is what causes the acceleration. Not just a motion, but it causes a change in motion over time, which is acceleration. So let's just run down of the two, comparing them side by side. So this is all the forces involved, and this is the net force. Net force right here, which would be 40 newtons. Okay, and then a free body diagram is very similar to a force diagram, but it just leaves out the object and everything else going on. So this would be a free body diagram. Take a look at that right there, this one right here versus that one right here. This just has the objects missing from it. And then looking at inertia, inertia is very important. The first law of motion from Newton's first law is a law of inertia. So think of that as the law of inertia. And that says something in motion, like this box right here, I'm trying to keep up with it. It's going to stay in motion. It's going to keep on going. It's not going to return over here. This is just an animation, but it's going to keep on going, keep on going. It's never going to stop. It's going to want to stay in motion because it has inertia. And this object at rest is not going to want to move because it also has a desire to stay at rest, and that's inertia. And then if there's an external force like this wall right here, all of a sudden the wall is going to be pushing back on this object. Well, it is going to change that motion because there is an external force, which is the force of the wall pushing back on the box, pushing on the wall, and that's going to cause a change in motion. And in this case, it's a deceleration. And then another thing to note is inertia is directly related to mass. If I was trying to change the motion of both of these objects, it would be much easier to apply the same force on this object. It would cause a much greater acceleration than applying the same force on that object, because this bigger object has more inertia or a desire to keep on doing what it was doing. In this case, it's staying in one place. It's at rest. But if it was moving, it would want to keep on moving. So that gets us into Newton's second law, and that's force equals mass times acceleration. Or in other words, force causes acceleration. Make sure you know that. It doesn't cause just motion, it causes acceleration, a change in motion. And that's going to bring us back to these equations. So you have your Vf equals Vi plus At, Vf squared equals Vi squared plus 2Ax, x equals Vit plus 1/2 At squared. And really this is a change in x, because you'd have to add the initial x if you had something going on and you want to find the end result. And then now we have two things to look at. When we have a problem, we are going to have to decide, do we start with forces and masses, trying to find acceleration, and then plug it into one of these equations? Once again, picking equations like we do. I'll show you an example in a second. Or are we going to do one of these equations and solve for A, and then we're going to need that to plug into this equation to either figure out force or mass? So let's start with a basic. We're going to go to the F equals ma equation. What is the force required to accelerate a 10 kilogram object by 3 meters per second? So F equals question mark, accelerate the mass equals 10 kilograms, and object is going to be accelerated by 3 meters per second squared. So what force is required? F equals ma, or F equals m10 times 3, and that is going to be 30 newtons of force. And then what is the force required to accelerate a 50 kilogram object? Well, we're going to have the same acceleration here, because I said it right here. And we're looking for force. Force equals question mark, A equals 3 meters per second squared. But our mass is 50 kilograms. So think about what that's going to do to inertia. Is it going to be easier or harder to get that thing accelerating? And it's going to be harder. And if you solve for it, it's going to be, let's go back. This one is 50 kilograms. So 50 times 3, and it's going to be 150 newtons. So it takes much more force because this object is bigger than that object right there. So which one has more inertia? Of course, it's going to be the 50 kilogram object, much harder to accelerate than the 10 kilogram object. So let's take a look at the next level of problems. And here you have how much force is required by the brakes of a car to stop a 1,000 kilogram car moving at 30 meters per second in 5 seconds. So these are all important facts, and they're going to give you these variables. You need to think about your variables, and you get this. We have force, mass, final velocity, initial velocity, and a time of 5 seconds. And then you have to determine, do you have enough information to start here or enough information to start here? And you'll find out that I have two unknowns here. I cannot start there. I have to start here. And so let's go ahead and use these givens to find the acceleration. And we have Vf, Vi, A, and T. And if you look at these three equations, this is the only equation that has Vf, Vi, A, and T. So we're going to start Vf equals Vi plus At, and I'm going to do the math like most of my students do, just so you can kind of compare. 30 plus, I like rearranging first, by the way, A times 5. You have to subtract the 30, so you get minus 30 over here equals 5A, and then I'm just going to flip the sides, and I'll put A over here. A equals minus 30 divided by 5, or negative 6 meters per second squared. So we found out the acceleration is this, and now we have A equals negative 6 meters per second squared, or a deceleration of 6 meters per second squared. And we are ready to do the second part, which is the F equals ma. So how much force is required? We have a mass of 1,000 kilograms, and we have a acceleration of 6 meters per second squared. So ignore that for the math. And you get 6,000, and once again, remember, force is newtons. And so that's how we do these problems. We decide where to start, and we go to if we start here, we go to there. And then in my next example, I'm going to show you the opposite way. So here we have, what is the final velocity of a 12,000 kilogram car starting from rest after 50 meters when 4,500 newtons of force is applied. And so we look at our givens, and our givens, when we look through this, we want to find A. A is like our intermediate. And here we have 2 out of 3, so we can find A here, whereas here we have 2 unknowns. We cannot find A using this information. And we get F equals MA, but we have to rearrange that for A. A equals F divided. Divide both sides by M, and we get 4,500 divided by 1,200. And our acceleration is going to be 4,500 divided by 1,200, and that equals 3.75 meters per second squared. So now we have acceleration of 3.75 meters per second squared, and we have to determine what equation are we going to use when we have VF, VI, X, and A. VF, VI, X, and A, nope, I can't use that, it doesn't have an X. And make sure you have your unknown included when you're picking your equations. VF, VI, X, and A, there you go. It's never going to be perfect. Well, here is close to it, where you can be solving for any of these variables. And so we're going to start off with VF squared equals VI squared plus 2AX. And once again, I'm going to solve the way my students usually do, which is they don't rearrange. They actually, you know, this is almost perfect. I'm just going to take the square root of both sides right now. And I'm going to start right here. Square root of VI, which is 0, squared plus 2 times A, which is 3.75, times X, which is 50. So what is the final velocity going to be? We plug all of this in, and 2 times 3.75 times 50 equals, and then take the square root of that answer, and we get 19.36 meters per second. And so that's going to be our final velocity in this equation, and that's pretty much it. This is my basic introduction to Newton's first 2 laws. Hope you